Hello friends, welcome you all to the 32nd lecture on functional analysis and its applications. In this lecture, we will discuss the applications of the parallelogram law. This is the content of today's lecture. Applications of the parallelogram law. Convex set. Let X be linear space, real or complex. A non-empty subset S of X is said to be convex if X, Y belonging to S. This implies that 1 minus alpha into X plus alpha Y belonging to S, for alpha lies between 0 to 1. Taking alpha is equal to 1 by 2, we see that if S is convex subset of linear space X, then xy belonging to S. This implies that X plus Y by 2 belonging to S. Applications of the parallelogram law. Theorem first. A closed convex subset C of a Hilbert space H contains a unique vector of smallest norm. Proof. Let D is equal to infimum of norm X such that X belonging to C, convex subset. Or this can be written as norm of X greater or equal to D such that X belonging to C. Hence, there exists a sequence Xn of vectors in C such that norm Xn tend to D as n tend to infinity. Consider two vectors Xn and Xm in the sequence Xn. Since C is convex, half Xn plus Xm belonging to C for Mn. Hence, using the definition of D, we have, definition of D, that is D is equal to infimum of norm X or norm X greater or equal to D for X belonging to C. Here, this one belonging to C, then by definition of D, we can write norm of half Xn plus Xm greater or equal to D, which gives norm Xn plus Xm greater or equal to 2D. Okay, because we know that norm alpha X equal to mod alpha norm X. Okay, so here alpha is equal to 1 by 2, that is 1 by 2 already positive. So this is 1 upon 2 into norm Xn plus Xm greater or equal to D. That is, we can write norm of Xn plus Xm greater or equal to 2D. This implies that here norm Xn plus Xm greater or equal to 2D. So this can be written as norm of Xn plus Xm square, norm Xn plus Xm square greater or equal to 4D square. Okay. So multiplying both sides minus 1. Okay. That is inequality reverse here. So this implies that minus norm Xn plus Xm square less or equal to minus 4D square. Equation 1. By the parallelogram law, norm Xn plus Xm square plus norm Xn minus Xm square equal to 2 norm Xn square plus 2 norm Xm square. So this implies that norm Xn minus Xm square equal to 2 norm xn square plus 2 norm xm square minus norm xm plus xn square. Okay. So minus xn plus xm square less or equal to minus 4d square. Okay. So this value is minus 4d square. Okay. So norm xn minus xm square less or equal to 2 norm xn square plus 2 norm xm square minus 4d square. Equation 2. Since norm xn tend to d as n tend to infinity, okay, norm xn tend to d and also norm xm tend to d as nm tend to infinity, we get from 2 norm xn minus xm square less or equal to 2d square plus 2d square minus 4d square, that is 0. Hence norm xn minus xm square tend to 0 as mn tend to infinity. This shows that xn is the Cauchy sequence in C. Since H is complete and C is a closed subspace of complete space of H, therefore C is complete because C is closed subspace in H. Hence the Cauchy sequence Xn in C is also a convergent sequence in C. Therefore, there exists a vector x in C such that xn converges to x as n tend to infinity. Since the inner product is continuous and consequently the norm is also continuous, we get norm x. Norm x is equal to limit n tend to infinity norm xn and also limit m tend to infinity norm xm, we can write, and norm xn converges to d. Okay, that is value of this and this is d. Hence x is a vector in C with smallest norm. Okay, because d is infimum of norm x. Uniqueness of x. Suppose x and y are two vectors in C such that norm x is equal to d and norm y is equal to d, then to show that x is equal to y. Since C is convex, therefore xy belonging to C, this implies that x plus y by 2 belonging to C. Hence, by the definition of D, norm x plus y by 2 greater or equal to D, so that norm x plus y greater or equal to 2D. Now, by the parallelogram law, we have norm x minus y square is equal to 2 norm x square plus 2 norm y square minus norm of x plus y square. Okay. Here norm x plus y greater or equal to 2d. So minus norm of x plus y square, that is minus 4d square with less or equal to. Okay. That is less or equal to 2 norm x square plus 2 norm y square minus 4d square. Here norm x is equal to d and then norm y is equal to d also. So this equal to 2d square plus 2d square minus 4d square, that is 0. Okay. So here norm x minus y square less or equal to 0. But we know that norm x minus y square greater or equal to 0. Hence we have norm x minus y square is equal to 0. that is norm of x minus y is equal to 0. Okay, we know that if norm x equal to 0, this implies that x is equal to 0. Okay, we know that this. So norm x minus y is equal to 0. This implies that x minus y 0. This implies that x is equal to y. Therefore, x belonging to C is unique. Okay, this completes the proof of the theorem. Next theorem. Let M be closed linear subspace of Hilbert space H. Let X be a vector not in M. Okay. Let D is equal to dxm. Then there exists a unique vector y0 belonging to M such that norm x minus y0 equal to D. Proof. From the definition D means distance between x and subset M equal to infimum of norm x minus z such that z belonging to M. Okay. Hence there exists a sequence yn in M such that norm x minus yn tend to D. Since M is linear subspace of H, yn belonging to M, this implies that half ym plus yn belonging to M. So by the definition of D, norm x minus ym plus yn upon 2 greater or equal to D, or norm of 2x minus ym plus yn greater or equal to 2D. Okay. So using the parallelogram law for the vectors x minus ym and x minus yn. So norm of x minus ym minus x minus yn square is equal to 2 norm of x minus ym square plus 2 norm of x minus yn square minus norm x minus ym plus x minus yn square. Okay. So this is x plus x, 2x minus ym plus yn square. Okay. So as this. So using equation 3, okay, that is this one. This can be written as, this is squaring both sides, that is norm 2x minus ym plus yn square greater or equal to 4d square. Okay, multiplying the both side by minus 1. Okay, so this can be written as minus norm of 2x minus ym plus yn square less or equal to minus 4d square. Okay. So using this inequality here, okay, this can be written as norm of 2x minus ym plus yn square. Okay. So this is minus sign. So we can write this is minus sign. Using this is less or equal to minus 4d square. Okay. So in place of this with negative sign, we replace minus 4d square. So norm of ym minus yn square, here x and x cancelled out. So norm of ym minus yn square less or equal to 2 norm x minus ym square plus 2 norm x minus yn square. This and this is less or equal to minus 4d square. Since norm x minus ym tend to d and norm x minus yn tend to d, we get from 4 norm ym minus yn tend to 0 because this is d and this is d. So 2d square plus 2d square minus 4d square cancelled out. So norm of ym minus yn tend to 0 as mn tend to infinity. Hence yn is a Cauchy sequence in M. Since M is closed subspace of the complete space H, M is complete, hence yn converges to y0 in M. Since norm is continuous function, so norm x minus y0 equal to norm of x minus limit n tend to infinity yn. As per the definition of limit, this can be written as norm limit n tend to infinity x minus yn. As per the definition of limit, again we can write this as limit n tend to infinity norm x minus yn, and norm x minus yn is d. So norm of x minus y0 is equal to d. Because here norm x minus ym converges to d as m tend to infinity. So limit n tend to infinity norm x minus yn is d. Thus y0 is a vector in M such that norm of x minus y0 is equal to d. Uniqueness of y0. To prove y0 unique, let z0 be another vector with this property. We shall show that y0 is equal to z0. Since M is a subspace of H, half y0 plus z0 belonging to M, hence by the definition of D, norm x minus half y0 plus z0 greater than D. So that norm 2x minus y0 plus z0 greater than 2D. By the parallelogram law, norm y0 minus z0 square can be written as norm x minus y0 minus x minus z0 square. So by the parallelogram law, 2 norm x minus y0 square plus 2 norm x minus z0 square minus norm of x minus y0 plus x minus z0 square. So as per this, again as above, this is norm of 2x minus y0 plus z0 square greater than 2d, that is square of 2d 4d square. So negative sign, norm of 2x minus y0 plus z0 square less than minus 4d square. Okay, so value of this is minus 4d square, and here norm of x minus y0 is equal to d. So putting the value of norm of x minus y0, that is 2d square, this is also 2d square, and this is less than minus 4d square. So total is this less than 2d square plus 2d square minus 4d square, that is 0. Thus, which implies that norm of y minus z0 square is equal to 0, that is norm of y0 minus z0 is equal to 0. Hence we have y0 is equal to z0, that is y0 is unique. This completes the proof of the theorem. Next definition. A normed linear space X is said to be uniformly convex if for every epsilon greater than 0, there exists a delta depending on epsilon greater than 0 independent of x and y such that norm of x less or equal to 1, norm of y less or equal to 1, norm x minus y greater or equal to epsilon. This implies that norm of x plus y by 2 less or equal to 1 minus delta. It follows from the definition that uniformly convex space is strictly convex. Theorem: every Hilbert space is uniformly convex. Let H be the given Hilbert space and epsilon greater than 0, norm x less or equal to 1, norm y less or equal to 1, and norm x minus y greater or equal to epsilon. Then by the parallelogram law, norm of half x plus y square. Okay, this is norm of half x plus y square. This can be written as this. Okay, so meaning of this is norm of x by 2 plus y by 2 square. Okay, so here two vectors x by 2 and y by 2. So this can be written as 2 norm x by 2 square plus 2 norm y by 2 square. So minus norm of x by 2 minus y by 2 square. That is this one. Okay. So norm x less or equal to 1, norm y less or equal to 1, norm x minus y greater or equal to epsilon. So this is half outside, that is 2 upon 4, that is 1 by 2. From this quantity also we have 1 by 2, and by this is norm of x minus y square greater or equal to epsilon square. Okay, this implies that minus norm of x minus y square less or equal to minus epsilon square. Okay, we have this is less or equal to 1 by 2 plus 1 by 2 minus epsilon square by 4. That is 1 minus epsilon square by 4. Now choose delta greater than 0 such that 1 minus epsilon square by 4 equal to 1 minus delta square. This choice gives norm of x plus y by 2 square less or equal to square of the 1 minus delta. So taking the square root of both sides, we get norm x plus y by 2 less or equal to 1 minus delta. Okay. Here delta independent of x and y, hence H is uniformly convex. In this lecture, we have discussed the applications of the parallelogram law. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naresi. Second, function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.